This is Arak, the beating heart of Iran's industry, a city that, in addition to its memorable and beautiful landmarks, is filled with factories and various industries such as petrochemicals, machinery manufacturing, and aluminum production. Because of this, the city not only has vast industrial capacities but also faces environmental challenges, making it one of the most sensitive points in the country in terms of pollution. This factory has many advantages, including creating widespread employment for the local population, producing a lightweight and highly useful metal for industries such as automotive and aerospace, and contributing to economic development and exports. However, alongside these benefits, there are also drawbacks. High energy consumption in the production process, generation of industrial waste, especially aluminum dross, and the serious issue of managing it are among the main challenges. Dross is a byproduct of the aluminum smelting process formed from impurities and oxide compounds. In the furnaces, pure aluminum is separated, while the impurities gather as a lighter layer on the molten surface and are removed as dross. So far, multiple solutions have been proposed to deal with this unwanted waste, such as remelting and recycling. But what is the problem? If this dross is not managed properly, it creates serious environmental issues. These solutions alone cannot fully address the problem and often bring their own challenges, such as air pollution caused by the energy needed for remelting or groundwater contamination at disposal sites. These problems are not limited to Iraq, they affect the entire world, especially in terms of air pollution. And time is running out to prevent further environmental damage. Our solution? Investigating the possibility of using aluminum dross as a partial replacement for cement in concrete. First, the raw dross is ground into finer particles. Then, different types are examined. White dross, which has passed through the furnace twice and is purer, and black dross, which has gone through only once and remains more impure. The ground dross is sieved to determine particle size distribution. In mixed design, different replacement percentages of cement with aluminum dross are tested: 5 percentages, 10 percentages, and 15 percentages, with the goal of finding the optimal ratio. To check reactivity, gray dross is mixed with water. In the initial reaction, vapor rises. Over time, the reaction releases hydrogen gas, producing visible bubbling. This shows that dross reacts with moisture, a factor that must be considered in concrete mix design. Durability tests are then performed. Concrete samples are subjected to freeze-thaw cycles to evaluate performance under harsh conditions. Chloride permeability is measured using RCPT to assess resistance against corrosive agents. Here, concrete containing dross on the right is compared with ordinary concrete on the left. Its appearance resembles a puffed cake with gaps forming between particles due to reactions between aluminum particles and moisture, shows more pores and is more porous. For closer observation, SEM imaging is used. These images reveal how particle size and reactivity of dross affect the microstructure of concrete. Finally, test results are analyzed with charts. As the percentage of dross increases, compressive strength decreases to some extent. However, 5% aluminum dross shows the best performance. According to research and experimental results, concrete containing aluminum dross performs better under high temperatures compared to concrete without dross, showing the least reduction in strength and the greatest environmental benefit. This approach reduces cement consumption, recycles industrial waste, and lowers the carbon footprint of concrete. The optimal point in our design is the percentage that achieves the least strength reduction and the greatest environmental saving, which is 5% aluminum dross. In the end, we have the best regards for your attention.